Hey, it's AP Chemistry time, and this is Miss Gray. We're going to work today in Unit 8 about intermolecular forces. So our focus today is to distinguish between the different types of intermolecular forces. So let's get right to it. First of all, let's talk about intramolecular forces. Notice the spelling here for intramolecular is different from intermolecular forces. Basically, forces within molecules, intramolecular forces, are called bonds, right? And one type of bond, the strongest type of bond, is a covalent bond where electrons are shared between atoms. Typically we find these when we have nonmetals that bond with nonmetals. Oh dear. My stuff is going away. All right, then the next kind of bond is called an ionic bond. It's about 85% the strength of the covalent network solid. So an ionic bond is the kind that exists when a metal bonds to a nonmetal. And it's a little bit weaker than a covalent bond. Finally, the metallic bonds are bonds between two different types of metals. And these are the weakest, with only about 65% of the strength of a covalent bond, because the electrons simply move freely throughout the entire structure. So those are the types of intramolecular forces. Now we're going to change our focus to intermolecular forces, the types of forces between molecules, not within molecules. So this is what we're talking about now. Intermolecular forces describes the interactions of molecules with other molecules. And when we look at intermolecular forces, we're talking about forces that are weaker than bonds. So they don't formally bind two molecules together, but they do produce a great impact that we're going to need to be able to discuss. Less energy would be required to overcome the force of an intermolecular attraction than a chemical bond, but that doesn't mean that they're not real forces that make an impact on the world around us. So if we're looking at an example of breaking an intermolecular force, something that's not a true bond, but an attraction nonetheless, then what we're looking at here is something like melting point. If we're going to break forces between molecules, then we might be pulling apart the solid particles so that they can move freely around one another. Or furthermore, we may be actually pulling them apart so much that they escape into the gas phase. And that's where we get boiling point. The stronger the intermolecular force, then the higher the temperature needs to be in order for us to melt something or boil it. There's 4 types of intermolecular forces that you'll need to know. The first type is called ion dipole. Then there's dipole to dipole. Hydrogen bonding is another type of intermolecular force. And then finally the one called London dispersion forces. So we're going to look at each of these individually. All of these are considered electrostatic attractions. In other words, these all come about due to the attraction that a negative and a positive species would have for one another. And so we're still working with Coulomb's law here. So an ion dipole force would simply exist between an ion, a charged particle, and the charged, partial charged that's on the end of a polar molecule. Remember that polar molecules are dipoles. In other words, a polar molecule has one end that's considered to be positively charged and one end that's considered to be negatively charged. And this establishes what's called a dipole moment. So we would be able to sketch the direction of the dipole moment when we draw the arrow from the positive towards the negative, right? That's how we sketch the dipole moment. So of these three types of particles, guess which one is considered an ion? It's the particle that has a charge all of its own. It's a charged particle. And then the dipole, of course, is the one where it has a positive end and a negative end. Two charges, but they're on opposite sides of the molecule, so it's considered a polar molecule. So that's what creates ion-dipole forces. Notice I've lined them up with the negative side pointing towards the positive ion. Suppose that I put a negative ion here instead. What if I change this sign? Well, then these guys would have to flip around, right? And line up the positive end of the dipole towards the negative ion, because that's the way electrostatic forces work. Like charges repel and opposite charges attract. Now, if we're looking at two dipoles together, then really we're talking about dipole forces. So we have the positive end of one molecule that's attracted to the negative end on another polar molecule. These are effective only when the polar molecules are close together, first of all. Remember Coulomb's law, radius is important, distance between charges, and also they have to be in the correct orientation, right? Because if I get the two wrong sides put together, they're going to repel, like charges repel. These are going to be weaker than the ion-dipole forces are, because the ion would have a formal charge, whereas a dipole has only a partial charge. Dipole-dipole interactions are going to involve both attractive and repulsive forces. This is another thing that weakens the dipole-dipole intermolecular force, is that when you get the wrong ends lined up together, they repel one another. So the molecules of equal mass and equal size would exhibit stronger intermolecular attractions when the polarity of that molecule is increased. Here's an example of what we mean by dipole-dipole interactions. So here's a molecule that's got a positive end on one side and a negative end on the other. So here's our positive charge, right, and here's our negative charge. So of course these two are going to line up so that we maximize the interaction between these two opposite charges. So they're going to get closer, and then we want to minimize the repulsive force between the two like charges, right? So we get those as far apart as we can. But what if these are not the only two molecules in the beaker? Chances are there's a whole bunch more, right? So they're going to line up in such a way that any repulsive force here is minimized between two negatives, and we maximize the attractive force between opposite charges. So that's how these particles in dipole-dipole interactions are governed by maximizing attractive forces while minimizing repulsive forces. So all the particles in the entire structure align themselves so that they can be in the most stable position possible. Now let's look at hydrogen bonding. The attraction between a hydrogen atom in a polar bond and an unshared pair of electrons on a nearby small electronegative ion or atom is going to result in hydrogen bonding. Electronegative. Wow, spelling. And typically by small electronegative atoms, we're talking about fluorine, oxygen, and nitrogen. So like ET, phone, home, yep, those are the three things. F-O-N, phone. Fluorine, oxygen, and nitrogen. If you don't have those for the hydrogen to be attracted to, then you're not going to have a hydrogen bond. The strong intermolecular attraction accounts for the high melting point and high boiling point, especially for something like water, or the high specific heat of water. And also the heat of vaporization tends to be very high in substances that have hydrogen bonding. This is a special kind of dipole-dipole attraction that tends to be extraordinarily strong and results in drastic changes in the properties of substances. It's strong because a proton, right, a proton is so much more massive in size than the electrons that we were looking at before. Protons in the hydrogen atom, for a polar bond is going to be very strongly attracted towards unshared electron pairs. This is also one of the ways we account for the fact that ice is less dense than liquid water because of hydrogen bonding. So let's look at an example of these physical properties. So if we look at this series for hydrides, then we're just going down the periodic table. Carbon is the smallest in its family, right? And then increasing in molar mass, we get silicon, then germanium, then tin. All of their boiling points are going to be increasing as the molar mass increases. Okay, now let's look at something that exhibits hydrogen bonding, where normally we would see this general trend upwards just like with the carbon family. This nitrogen, because it has the ability to form hydrogen bonds, is going to have a much higher boiling point than what fits the pattern, because these electron pairs right here are going to be attracting the hydrogens on other nearby ammonia atoms. Right? This hydrogen is going to have an attraction for the lone pair electron. Okay, now let's look at what happens when we have, say, oxygen. When oxygen's bonded to the hydrogen, then we get a dramatic increase in the boiling point. For water, the boiling point is 100 degrees Celsius. I know you already knew that, but look how it does not fit the pattern for the other elements in its family. They start out low and increase as the molar mass increases, yet water is the smallest and it has the highest boiling point. That's because of the ability of water to form hydrogen bonds, where the lone pairs on the oxygen attract the hydrogens from other water molecules. Do I need another pair? I do. I need another pair. Yikes, that's a lot of electrons. Okay, here's hydrogen fluoride, also forming hydrogen bonds, kicks this one up out of the pattern that we normally would see in the boiling points. When hydrogen bonds form in water, here's what I was drawing earlier. What we're looking at is a polar molecule, because the lone pairs of oxygen are hanging out on this side, and then it's sharing electrons with the hydrogen. So that sets up this negative end on this direction and a positive end on this side of the molecule. And it's not a formal charge, it's just a partial charge, but it's powerful enough to cause the water molecules to line up so that the negative end of one molecule lines up facing the positive end of another molecule. Remember when we were running around in the classroom pretending to be water molecules? This is where that becomes really super important. The attraction and repulsions for positive and negative charges is a really important factor in determining physical and chemical properties. Now let's look at London dispersion forces. Basically, this is an attraction that's based on the location of an electron in one molecule to the electron location on a different molecule. This is a much more subtle force, but if it were not for this force, London dispersion forces, then we would never have nonpolar solids or liquids, because then nonpolar molecules would not be able to exert any force upon one another. But due to London dispersion forces, there's nonpolar solids and liquids such as oils and fats and waxes and things like that. So London dispersion forces depend on an instantaneous dipole moment. So at any given instant, part of the charge is shifted for just a moment to one side or the other of the molecule. And this can be induced by its interaction with other molecules nearby. So suppose that we have this molecule of oxygen, where notice there's a lot of lone pairs surrounding this molecule that are not bound in the bond. And now suppose that for just an instant in time, the electrons that are over here shift slightly in this direction. So now they're spread out just a little bit extra. And so we have a momentary dipole set up where there's more negative concentrated on this end of the molecule than there is on this end of the molecule. So it's a partial positive on one side and a partial negative on the other. And so the molecule next to it gets induced in the same direction, where now this positive charge is pulling more electrons this direction. And so that sets up in the neighboring atom, or the neighboring molecule, a partial negative and a partial positive, which would then influence the thing next door to that molecule. So that's how the dipole moments can be induced and cause an attraction. So if there's more electrons available, then we would call it a more polarizable molecule. You could think of this in terms of having squishy electron clouds. The more electrons there are available to shift around, then the greater London dispersion forces they will be. And so this is completely going to be dependent on the molar mass. In other words, the size, right? The size of that particle. This force tends to increase with increasing molecular size. Oh, I put the wrong word in here. This was meant to be shape. Aha. See, I'm messing up. All right, so the shape of the molecule is going to determine where the electrons exist, right? Well, they determine the shape. So the more lone pairs, the different types of shapes they will be, and then that's going to create more polarizable molecules, and then the force increases with an increasing molecule size as well. But these tend to be weak forces, and they don't last very long. The dipole is considered instantaneous, so it just lasts for an instant. It would last longer when we slow the molecules down. So at lower temperatures, temperature, how come I can't spell temperature? Wow, temperature? Yeah, okay, you guys know how to spell temperature. Spell it right and tell me later. Normally I can spell, don't worry about me. This also is going to help us then explain the trend for bigger molecules to have higher melting points and boiling points. Like what we just saw in the graph, that as methane and silicon and germanium are all compared in their boiling points, the boiling point increased for each of these compounds as we went down that row in the periodic table. So the bigger ones have higher boiling points and higher melting points as well. These are much, much weaker forces than all of the other forces. In fact, they have a special name. You may remember this guy from the gas law unit, van der Waals. These are called van der Waals forces. Remember, he's the one that helped us distinguish between ideal gases and real gases. And the things that determine how gas particles are less ideal is the attraction of particles, in other words, the charge, like where the electrons are, and also the size. So those were the two important things in the van der Waals equation. Well, that's why these are called van der Waals forces. So let's look at an example. I have two molecules here, well, two atoms, where you can see the nucleus is shifted slightly. So before I showed you an example of electrons shifting around, but suppose that the nucleus shifted around a little bit too. So if the nucleus is no longer directly in the center of the atom where it's supposed to be, but now shifted over here, then what does that mean? That means that there's a partial positive charge to the right side of this molecule and a partial negative charge on the other side, on the other direction. So then what that does for the neighboring atom is that it pulls the electrons more towards it and creates a partial negative in the neighboring atom. So it would work the other way too. If we took our nucleus from the center and had it shift over or vibrate across out of the middle, then that's going to create this partial negative and a partial positive that induces a similar type of charge in the neighboring atom. So let's summarize that with words. First of all, the vibrations in the nucleus within the electron cloud created a temporary dipole, which we show using the partial positive and the partial negative charges. This causes then sympathetic vibrations in the nuclei of the neighboring atoms, so that a partial positive and partial negative charge becomes arranged opposite of one another. The plus gets near the minus and the minus near the plus. So now there's an attraction between the induced dipole of opposite partial charges on neighboring atoms, and this is what creates the van der Waals force. Eventually, all of the atoms and molecules vibrate in unison then, and it makes the partial charges actually add up to enough force that it holds the entire structure together. When enough energy is given to a substance that is held together only by van der Waals forces, then those forces can be easily overcome and the compound will boil or melt, depending on its phase. All right, so now let's look at some alkanes, straight chain hydrocarbons. So, of course, we know this guy's name is methane. He's got one carbon, and it's a pretty small molar mass, comparatively speaking, and its boiling point is negative 161 degrees Celsius. The only way to explain what's holding this together in a nonpolar molecule is London dispersion forces. There's no other charges or dipoles that would hold this together. But look what happens when now I have a bigger molecule. In ethane, the boiling point is negative 89 degrees Celsius. And then propane boils at negative 44 degrees Celsius. So as we get bigger, the boiling point increases and increases and increases. Finally, I've shown hexane here. Normal hexane in a straight chain has a boiling point of 68 degrees Celsius. So at room temperature, hexane would be liquid, right? Then as we increase the number of carbons, I've shown 6 here, like paraffins have up to 20 carbons. 20 carbons and more are paraffins, which is wax, like what candles are made of. They are low melting point solids. And then asphalt has 36 carbons and more that can only produce gummy residues. They don't actually boil, which is good because then we can use them on things like our roads, and they can get hot, but they can't actually boil away. So let's look at a chart to help us decide which intermolecular force is the most important one influencing a particle. So the first question you'll ask is, are the interacting particles molecules or ions? So, are ions involved? If the answer to that is no, then the next part of the question is, are polar molecules involved? So remember, to decide if something's polar, you need a difference in electronegativity and you need a geometry that won't cancel. All right, so if we say, no, it's not a polar molecule, it's nonpolar and there's no ions, then the only type of force this could be is a London dispersion force. For example, argon or iodine. Okay, what if the answer is yes? There are polar molecules involved. Well, then we have to answer another question. If there's polar molecules involved, then are hydrogen atoms in those molecules bonded to an oxygen, a nitrogen, or a fluorine? If that answer is no, then this is just a simple dipole-dipole interaction. But if the answer is yes, that hydrogen atom's bonded to oxygen, nitrogen, or fluorine, then those three atoms, the elements oxygen, nitrogen, or fluorine, they're going to hog the electrons so much to themselves that they allow for hydrogen bonding, right? Okay, now suppose that there are ions involved. There's two possibilities here. Are polar molecules and ions both present? If the answer is yes, then that's an ion dipole force. For instance, if we dissolved potassium bromide in water, then that interaction would depend on ion dipole forces. But if the answer is no, that there's only ions present, not polar molecules, just ions, then that's simply considered to be an ionic bond, which is not an intermolecular force. Remember, bonds are intramolecular forces. All right, so that's how we would decide what type of intermolecular force is at play. It's called IMFs, and we're going to talk a lot about IMFs and how they influence the properties of matter. That's it, guys. See you soon.